last speaker, we are going to switch our view to Europe, and I'm going to invite the Dr. Emilio CALVANESE Strinani, CEA Leti of France. Please join me. Welcome, Dr. Strinati.
Good afternoon, good morning. My name is Emilio CALVANESE Strinati, the Future Wireless Systems Scientific Innovation Director at CEA Leti, the 5G All-Star and the RISE 6G Coordinator. I'm honored to share with you the vision of CEA Leti on the future wireless system that will shape our life at the horizon 2030. In 1926, the visionary Nikola Tesla stated, "When a wireless is perfectly applied, the whole Earth will be converted into a huge brain." By the year 2030, responding to fundamental human, societal, and economic needs, and based on the expected progress on information and communication technologies, Tesla promise may become a reality. 6G will play a significant role to provide an ICT infrastructure that enables end users to perceive themselves as surrounded by a huge artificial brain, offering virtually zero latency services, unlimited storage, and immense cognitive capabilities. New services and new use cases will appear, driving the evolution towards 6G. As an example, 5sense interactive hologram technology that will teleport people from one place to another on the Earth, and why not support the connection between interactive 6G sky services, or interactive haptic communication, human to human, human to machine, or even machine to artificial intelligence, also between different generations of people that will be able to interact together through haptic communication, enabling, for instance, in Industry 4.0 context, new operational experience and remote monitoring, control, or maintenance. The new service will set new challenges to technology with drastic performance improvement needs. Latency will have requirements on order of milliseconds, either microseconds. We'll need to do self-designing joint communication, computation, and caching and control optimization jointly together in order to attain overall effective tasking and actuation. We'll need ultra-high capacity links of the order of terabit per second, either tens of terabit per second, and we need also to change the way we design and optimize the network and its services, changing from stochastic optimization, where the network is designed to meet the requirements in average capacity, average reliability, average latency, any kind of these bounds, to deterministic network and service optimization design, targeting to meet the requirements for specific setting of user, communication channel instance, and network configurations. Today we have a clear first roadmap towards 6G, a first phase of unconstrained research and development started a couple of years ago and it will last until 2022-2023, which is scouting and testing the potential of key enabling technologies for the next generation. Then a second phase on 6G key technology components and design, ending with another phase of 6G testbed and testing. That actually will drive us to have products of 6G and services at the year 2028 to 2030. Today we have a first clear vision on the key performance indicators towards 6G. Following the even more approach, we ask the technology to provide a factor of 10, 100, 1,000 of improvement in terms of link capacity, latency reduction, improvement of connectivity reliability. But 6G will not only be a service and a network to provide service support on the ground, but also in the three-dimensional space, serving drone-assisted logistics or taxi drones, and providing navigation and intelligence support or even entertainment on the 3D. This will require to improve the uniform user experience not only on the 2D, but also in the 3D space. 6G will introduce also new constraints on jitter of latency, need to attain determinism on the network operational services. Extreme energy efficiency, targeting a picojoule per bit to attain almost zero energy consumption. setting localization precision targets on the 2D, but also on the 3D for new types of services in the 3D space. By looking to those KPIs, the question is, can we achieve them? Which are the new technology advances or disruption that will enable the future 6G network and service? With 6G, the new perspective is to look into the network as a truly pervasive competent system, enabling new interaction among humans and machines and intelligent services with sustainable cost in an economical and ecological terms. 5G already represents a significant step toward this direction. 6G will take this perspective as a driving paradigm. Therefore, designing and engineering 6G, new KPIs will come into play, such interference reliability or energy per goal. Of course, there's no single number for those KPIs. It will depend on the specific service. There is also another fundamental question: how to sustain all this data being generated, crossing the network, being processed and stored. The projection of the data follow an exponential growth. By 2035, 9 billions of connected people will be on Earth, trillions of connected devices, wireless communication and AI assistance will be considered as a commodity. The cyber and the physical space will fusion, turning humans, things, and events into information. If you continue doing as we do today, the world data chain will consume about 20% of the world energy in 2035. The other approach would be to go for a degrowth, but this is clearly not a potential choice, seeing all the benefits we have today with ICT technologies. The real question is, how can we achieve something intermediate? With sustainable growth, limiting and distilling produced data with edge AI technologies, limiting the energy consumption with innovative other technologies, exploring new materials, new hybridization approaches, storing, communicating, and processing data with new paradigms. In a recent study from MIT, it has been evaluated that training a single AI model can emit as much carbon as 5 cars in their entire lifetime. The good news is that wireless networks have already been working on energy efficiency and transmitted data. Already in the 90s, with the second generation of communication system, which actually was the first one conveying data in the network, we start evaluating the energy needed for the transmission. At that time, 40 kilowatt hour per gigabyte were required. Then, with improvement of technology, we'd reduce this number, arriving to today with 5G to have tens of watt per hour per gigabyte. Now consider that we have the technology in 5G and we freeze our knowledge. To feed all the energy required in the network with the 5G technology as the data we have today in 2020, we'll need to cover the entire Mexico with the photovoltaic panels. In 2025, the entire surface of Australia. In 2030, the entire North America, Canada plus US. In 2035, Asia, Antarctic, and Africa. In 2030, either twice the surface of the world would not be enough. Starting from the new hardware design, a new way to operate the network, we need to look at disruptive way to save energy and reduce the data being generated, crossing the network, processed and stored. The other good news is that we have not stopped looking at new generations of energy efficient solutions for the wireless networks. We have already started researching on new hardware, network management, exploitation of artificial intelligence algorithms, and smarter use of data to improve the energy efficiency of the wireless network. As today, the forecast of our results is that we can achieve a factor of 100 in terms of energy efficient improvement at the horizon of 2030. Therefore, given the results, the research we are doing in terms of energy efficiency, given this factor of 100 at the horizon 2030, we will be able to equip only, and I'm saying only in a very ironic way, the surface of France with photovoltaic panels in order to feed all the energy needed for the data crossing to the network. In our vision, there is a technology expectation shift which is expected at the horizon 2035. we start for a vision of more targeting performance in 6G with an improvement of factor 100, 1000, or reduction in terms of, for example, latency of factor 10, and so on. But there's another side of the story, which actually how to meet the societal needs, how to provide a network which has the needed energy efficiency, which can provide a low end-to-end environment impact, which can provide security, resilience, or either awareness about electromagnetic fields and digital inclusion. This new perspective set a new set of trade-offs in terms of performance versus societal requirements that will shape a new way to design the system. New generation comes from the crossing between the technology breakthrough which are ready at a given time, and new service application use cases cannot be served in an efficient way from the previous generation. We have a clear view of key enablers, technology breakthrough that will be needed for the next generation as up-to-rest communication, support of distributed artificial intelligence, new type of antennas, and so on. Also, the new service application that are foreseen at the horizon 2030, 2040. More approach in terms of design the network, setting KPIs just for having more performance is not enough. It's a clear point that we need to find a way to design sustainable 6G networks. Therefore, the design of future 6G network is not just targeting a factor X in terms of performance improvement, having a raise on new hardware design, new artificial intelligence technologies, new network management and operations, but also to support sustainable evolution of society and economics. This will require to rethink the whole data generation to use chain. Among the many technologies that have been investigated for 6G, terrestrial and visible light communication related are fundamental to provide high capacity links, high bandwidth, to have the potential to fully exploit small antennas and focus beams. There are a lot of challenges related to this, as for example, new hardware design in terms of power amplifier, in terms of connection losses between antennas and power amplifier, the high propagation losses, the blocking, the limited coverage. In order to attain terabits per second, we are speaking about coverage of tens of meters. There's also the other potential about the 3D network and networking, where we'll be able to provide ubiquitous 3D wireless connectivity and intelligent support for pure 3D services. And that will be a huge set of challenges in terms of energy efficiency or the data chain, the effective cooperation strategy of mobile aerial devices, the extension of the edge cloud to a 3D cloud through drones, low orbit satellites, and so on. There's also the huge challenge about the energy harvesting and the low power operation. In order to reach zero energy transmission of the order picojoule per bit, for achieving an energy sustainable operation of the network, the distributed artificial intelligence, but also the federation of knowledge sharing, in order to speed up the learning in new scenarios, and also to enforce the privacy of shared data. It will be also important to have techniques assessing the value information, intelligent autonomous selection of information to collect, communicate, process, and store the data. Also the use of intelligence reconfigurable surfaces, enabling wireless environment as a service and constitution of what we call the boosted area, where we can choose to improve the performance in terms of link capacity, energy efficiency, low electromagnetic fields, and so on. Following the high-performance approach driving the terabit per second capacity in the links, will require to explore new frontiers of wider bands from 90 gigahertz to 300 gigahertz, and even higher with the visible light spectrum. At those frequencies, there are several issues. Today, we know how to prototype hardware with acceptable energy efficiency of the order 10 to 20% at low D bands, let's say up to 130, 160 gigahertz. But going higher, CMOS technology results in not being adapted to output the need power. BCMOS present a very high cost and they meet energy targets up to 160 gigahertz. There is indeed a dead valley between 160 and 300 gigahertz. The challenge is severe when we target the IC designed for high power, performance selectability, and isolation, and Fmax among others. New transistors, new hybridization, opportunistically mixing materials to profit of their different advantages and compensate the limitation are today a challenge topic of investigation, and at CA we are taking this challenge. There's another issue also, that going to higher current frequency, losses in the connection between the RF and antennas increase too. As an example, a factor of 100 of increase of losses is experienced comparing millimeter wave frequency to higher bands. And this is measured in our prototypes. At CLT, we are investigating the co-design and integration of RF and antennas to limit those losses. Indeed, exploring the high bands of 6G will require, in addition to the B-alignment techniques, the resource allocation techniques, and also to techniques that contract blocking and other networking solutions, will require to develop new technologies being low cost with high energy efficiency. Another promising technology for future 6G networks are the reconfigurable intelligent surfaces. Those are surfaces endowed with the capability of actively modified and ping electromagnetic fields. At CA, we have been working a lot on this technology and leveraging for the knowledge we already have on antennas array. We are producing the first prototypes at 60 gigahertz, 80 gigahertz. Now, a huge technology challenge is to go beyond such frequencies like 140 gigahertz, either 300 gigahertz. The adoption of reconfigurable intelligent surfaces in 6G will enable a new concept, which is the wireless environment as a service. The idea is that we can create boosted areas for high connectivity, high localization precision, high secrecy, high energy efficiency, or low electromagnetic field on demand in a specific location without modifying the entire network deployment. To this end, there's a project that's been just accepted from the European Commission, the RISE 6G project, which I have the honor to coordinate, that will focus its attention on the design, the testing, and the hardware production of boosted areas. To conclude, communication has been the basic commodity for every wireless generation. The boundary between the computer science, artificial intelligence, and telecommunication is disappearing. Society and industry are becoming more and more data-centric, data-dependent, and automated, having the cyber and physical space fusioning and turning humans, things, and events into information. We need disruptive concept to attain the sustainability targets at the horizon 2030, and to this end, it's time to investigate the path for sustainable 6G networks. Kamsahamnida. I would like to thank you for your attention. And here I listed 3 new journal papers where you can find details of what I spoke today in my presentation. Thank you very much.
Thank you, Dr. STRINATI, for his nice presentation. So I cannot wait to see the continued cooperation between Korea and the European Research Institute.
Thank you. I hope all of you enjoyed our first 6G Global 2020 a lot today. On behalf of 5G Forum, I'd like to take this opportunity to thank amazing speakers and panelists for sharing really in-depth thought and vision about 6G. And I think it was a really nice moment to share all the visionary talks, which is too much for today. You know what? We are going to continue to return all these topics in the next several years ahead. So next year, we're going to have the better chance to discuss much about 6G tech and also how operator and many other stakeholders view kind of a commercial side. So we are looking forward next year, the 6G Global 2020 and next year. So we are looking forward to 6G taking 6G, vision and service, and everyone is taking its course toward the 2020 together with many international partners. So I will see you next year at the second 6G Global 2021. Thank you so much.